Okay, we start off with the chapter linear programming problem, and in this class we are just going to cover up the whole chapter taking few examples, and there is not much to discuss about it anyway. Well, obviously there is a lot to discuss, but uh, we are just going to keep it simple. Now, what is a linear programming problem? So let us first understand that. Now, linear programming problem, the word linear means that all the variables involved are linear. Fine. So whatever kind of variable that which we are going to work with, they are all going to be linear. So their power is going to be 1. Programming, obviously, programming means here that you can be given a situation, a real world situation. You may not be given the direct problem. You may be given a situation which we have to transform into or model into a problem. Now we are going to see how the problems are modeled. So that is why it is called programming and problem, obviously. That's what we have in this chapter. So now to begin with, what does linear programming problem do? It does what? It takes a function which is generally denoted by z, which we call as the cost function or profit function depending on the problem, right? In general, it is called an objective function. Objective function means that this is the main function on which we are going to work. Now, this function as given, we will try to optimize it. Optimize means either we are going to maximize it or we are going to minimize it. Fine. Now, if it is a cost function, say you are trying to calculate cost of something, cost of raw material, cost of transportation, cost of anything for the matter of fact. In that case, we will always try to minimize the cost. But in case if we are talking about profit in the sense, say profit of sale or any profit turnover, in that case we will always try to maximize the profit. Fine. So now, how does an objective function look like? Now, in our syllabus, we have two variable linear programming problems. So we are just going to work with two variables. So if z is our objective function, and let us consider the two variables x and y, which we call as the decision variables, then z will look something like ax plus by plus c. There can be a c as well. In some problem there can be a c, in some problem there may not be a c. So it is, as you can see, is a linear function of these two variables, and that is the reason why they are called linear programming problem. Now, along with that, any problem must have certain restrictions. Restrictions in the sense that we are trying to optimize this particular function. Optimize in the sense we are trying to maximize or minimize this particular function given there are certain restrictions, and those restrictions are called as the constraints. They are called the constraints. Now these constraints are generally linear equations or inequations in the variable x and y. So the constraints may be like some a1x plus b1y equals to c1. Obviously a1, b1, c1 are different from a, b and c in the objective function. Or it can be a2x plus b2y less than equals to c2. Now obviously this less than equal to can be less than equal to, greater than equal to, less than greater than. It can be any sign of inequality. Fine. And the most important constant, that is x has to be greater than 0, y has to be greater than or equal to 0. Why? Because linear programming problem generally deals with real world problem, and in real world problem quantities can never be negative. So therefore it is necessary for us to consider that the variables, the decision variables, has to be non-negative. It has to be non-negative. Fine. So now let us see how we write one linear programming problem, a model of linear programming problem. So it will look something like this. Say first I have to write what kind of problem it is. Either I am trying to maximize the problem or I am trying to minimize the problem. So I will be writing max or min depending on what type of problem it is. Then we will be writing the objective function, whatever the objective function we are given. So let it be ax plus by plus c. Fine. Then I have to write the constraints. So constraints has to be, before we write the constant, we write this subject to maximum. So when, let me just finish it off, then I am going to tell you how to read this. So it will be a1x plus b1y, say less equals to c1, a2x plus b2y less equals to c2. There can be n number of constraints obviously, but I am considering that for our consideration, let us say that we have two different constraints, and obviously the third constraint will always be this. So this is a model of an LPP. So this is a model of LPP. Fine, right? So how we read this? Say if the problem is saying max, so if we are trying to maximize, then we say max z equals to this, subject to the constraints this, this and this. Fine. Now you can be given two different types of problem. That is, you can be given this problem directly, that is you are already given the modeled problem, or you may be given a textual problem, a word problem, where you will be given all the different criterias and the whole situation. From there you have to model the problem, right? So let us take a sample problem and let us understand how to solve it, and then we will be going into modeling the problem. Okay, so let us take this small problem. Say this max z equals to 60x plus 15y. I am just taking a random example, whatever I can see right in front of me, subject to x plus y less equals to 50, 3x plus y less equals to 90, x and y greater or equals to 0. So this is the problem, right? This is one of the problems. Now how to solve these problems? Now whenever I have got two variables, my solution is always going to be graphical solution. Fine. So in that case, if you are attempting this type of question, you will be provided with graph. You have to solve it in a graph. So now the first thing is that you have to draw a graph. Fine. So in the graph we don't require the negative side, obviously, because all our calculation will be in the first quadrant only. Now this is x-axis, this is your y-axis. All I need to do is draw these two constraints. So let us take the first constraint. Now how to draw the inequalities, if you remember from your class 11 knowledge, x plus y less equals to 50. So let us first consider x plus y equals to 50. Fine. So now writing it in the intercept form, this is x by 50 plus y by 50 is equals to 1. Right? So therefore, somewhere here there will be 50 comma 0, somewhere here there will be 0 comma 50, I am very sorry that, yeah, so this is your first line, but now this is the line this, but I am talking about this less equals to. So what to do? Put origin in this. So 0 less equals to 5, obviously it is satisfying, so therefore it is this direction. Right? Then 3x plus y less equals to 90. So x by 30, y by 90. So here somewhere there is 30 comma 0 and somewhere here 0 comma 90. Once again, if I put origin here, it is satisfying. So therefore, it will be this side. So therefore, the common region that I got is this. Right? So now, just to ensure that we don't confuse, let me remove this. All you can do is just mark the common area, and for the individual lines you can just mark it with an arrow. If you just mark it with an arrow, that signifies in which direction the area is. Fine. Now in this common region is called the feasible region. This common region is called the feasible region. Feasible means that the possible solution to the problem will always lie in this particular region. So therefore it is called a feasible region. Now there is a theory. We are not going in details into the theory. The theory suggests that the solution to an LPP will always lie at the corner points of the feasible region. So what are the corner points? Corner point means this is one corner point, this one is another corner point, this is one corner point, and this is the fourth corner point. So there are 4 corner points. Now of which 3 of them we already know. The fourth one we don't know. How to find that fourth one? Now 2 ways. Obviously, if you have drawn the graph correctly, you can directly find it from the graph. Else you can solve these 2 inequalities. Now not considering them as inequalities, you can solve them directly considering them as equalities, and whatever is the point of intersection you get, that is your this fourth corner point. So let us find out. So what are the things you are given? Now obviously the graph you are drawing in the graph paper, and all these calculations you are doing in the copy or in your answer sheet. Now remember, whenever you are doing this, do mention the points. So for this, the points will be this will be 0, 50 and 50, 0, like you have done in your junior classes. So 3x plus y is equals to 90, x plus y is equals to 50, cancel, cancel, this is 40, this is 2x, x is 20, right? So if x is 20, y is 30. So therefore, this point is 20, 30, right? Now comes the main part. Now let me just erase the problem. We have already understood this part, so we don't need this anymore. Now let me just this side also. Now we have to draw a table. What is that table? The table will contain two columns. First side, it will be corner points, and on the right side it will be value of z. Now remember, what was z? I just erased it. Z was 60x plus 15y, right? So corner points, what are the corner points? Let us write that first. The first one is 0, 0. Okay. The second one is 30, 0. Third one 0, 50. And the last one 20, 30. Fine. So now put these values into z and check what values you are getting. So if you put 0, it gives you 0. If you put 30, 60 into 30 gives you 1800. 0 into 50, 15 into 50 is 750. And if you put 20 and 30, 20 is 1200 and 30 into 15 is 450. So therefore 16 to 20, 1200 plus 450, that is 1650, right? I hope I am doing the correct calculation. Let me check it for once. So 0 is this, 30, 0, 30 into 61, 1800, 0, 50, that is 750, and 20, 30, 1200 plus 450, that is 1650. Fine. So now the question was to maximize. So now I have to check for which one of them is the maximum value. So therefore, this is our maximum value, right? So therefore, our solution is, so therefore, how to write the answer? Z is max at x equals to 30, y is equals to 0, right? Fine. So this is how we solve an LPP. Now, once we have understood that how to solve an LPP, now comes the different types of LPP, that how many different types of LPP we have. So let me just write them down. Okay. So the first problem is, you can have a manufacturing problem. Manufacturing problem. manufacturing problem, then we have diet problem, third we have allocation problem, and fourth we have transportation problem. Fine. Now obviously of all these four different types of problem, this one type of problem which is a little bit different and it takes a little bit of our understanding, but for this first three types of problem it is almost all the same depending on what kind of problem it is given. Now in manufacturing problem it can be a maximization problem, it can be a minimization problem as well. Okay, so manufacturing problem, how it can be two different types. Say if in the manufacturing problem you are trying to say maximize the profit of the manufactured product, then it becomes a maximization problem. But if you are trying to say optimize the cost of the raw materials, then it becomes a minimization problem. So always what matters is, are we talking about the cost or are we talking about the profit? In any case, transportation problem in one hand is always a minimization problem. Why? Because we are always trying to minimize the cost of transportation. So that is why transportation problem will be always a minimization problem. But for these three different types of problem, it can be either a maximization problem or a minimization problem depending on what it is given, right? So now let us take an example. Now the example that which I am going to take is going to pop up on your screen. I am not writing the example here because it's a room full of example, like I have to write a lot. So I am just taking up the problem which will be popping up on your screen. Check it first and then we will come back here and we'll solve it. So if you have seen the problem, now let me begin. So the problem that which we are doing is a manufacturing problem. Now the problem says that a small firm manufactures item A and B. The total number of items that it can manufacture in a day is 24. Item A takes on, it should be an hour to make, while item B takes only half an hour. The maximum time available per day is 16 hours. If the profit on one of the item on one unit of item A is rupees 300 and that on unit of item B is rupees 160, how many each type of item should be produced to maximize the profit? So it's a maximization problem. So you can see it's a concept about manufacturing and you are trying to maximize the profit. Now first I need to understand what is our objective, what I am trying to maximize. I am trying to maximize the profit. So therefore my problem will be max Z equals to, now profit on what? Profit on production of units of item A and units of item B. So let us consider units of item A produced be X and units of item B produced be Y. So these are the two variables that I have to consider. So if I am producing X number of item A, so there for each the profit is 300. So on X number of item A, the profit will be 300X. plus 160 is for item B. Now the constraint, subject to. Now subject to the constraints, what are the constraints? The total number of items that can be produced in a day is 24. So it doesn't matter how many items of A and B you produce, you can't produce it more than 24. So therefore x plus y is less equals to 24. So either you can maximum produce 24 or less, but not more than that. Then the total number of hours that you can spend on producing the item, that is 16. Now on every single single unit of item A, you require 1 hour. For every single unit of item B, you require half an hour. So therefore on x number of item A, you require x hours, and y number of item B, you require y by 2 hours, and that total has to be less than or equals to 16. So these are the two constraints. And now obviously x and y are number of items, so that can't be negative. So therefore x has to be greater than 0, y has to be greater than 0. So this is my problem. So now you understand how to model a linear programming problem. Fine. Now my job will be to solve this. Now the process is all the same, so we have to draw a graph. So let me just quickly draw the graph here. So x plus y is equals to 24. So here there is some say 24 comma 0, and here there should be 0 comma 24. Okay, say this is 24 comma 0 to be precise. Fine. Now this is x by 16, y by 32. So x by 16 somewhere here and y by 32 will be somewhere here. So let me just first draw this. Yeah. So this is 0, 32. This is 16, 0. Now for both the cases it will be towards the origin. So therefore my feasible solution or feasible region is this. Now need not be necessarily that the feasible region has to look like this always. Now obviously I don't know this fourth corner point. I need to find this fourth corner point by solving these two simultaneously. Now if I solve them simultaneously, x and x cancelled, y minus y by 2, that is y by 2, 24 minus 16, that is 8. So 2 goes on the other side, y is 16. So therefore y is 16, so x is supposed to be 8. So I got the point, 8 comma 16. Now you can do it to show the calculation, please. I am not showing the calculation, which is obviously because of the constraint I have with this board. So please ensure you show this calculation how you are getting this 8 comma 16. Now let us draw the table. So corner points and value of z. So corner points, let me just write it down. So 0 comma 0. Then obviously you see 0 comma 0 doesn't contribute anyway, but ensure you write it. Then I have 16 comma 0, 0 comma 24 and 8 comma 16. Right? So this is all I have. Now in the first case it is 0. If I put 16, that is 4, 8, 0, 0, 16 into 3, 48, 24 into 16, 4, 12 and 2, 44, 24. So that is 4, 8, 3. So that is 3840, and 8 comma 16, that is 2400, and 16 into 160, 2560, 0694, 4960. So this is max, right? So therefore your answer will be, for max profit, the firm need to produce 8 units of A and 16 units of B. And also you can write what is the max profit. So the max profit is rupees 4960. Fine. So this is one problem. You have seen the second problem on your screen. Now let us start off. Now this is a diet problem. Diet problem means where you are buying few food products, food items, and you are mixing it, and you are trying to find the minimum cost of doing so. So Kellogg is a new cereal formed of a mixture of bran and rice that contains at least 88 grams of protein and at least 36 milligrams of iron. Knowing that bran contains 80 grams of protein and 40 milligrams of iron per kilogram, and the rice contain 100 grams of protein and 30 milligrams of iron per kilogram, find the minimum cost of producing the new cereal if bran costs rupees 5 per kilogram and rice costs rupees 4 per kilogram. So now here I have to buy bran and I have to buy rice. So let x kgs of bran and y kgs of rice to be bought. Fine. Now, so our problem becomes min. Let me do something. Let me just shift it a little bit. So let me write here. Min z equals to x kgs of bran. Bran costs rupees 5. So that is 5x, and rice costs rupees 4 per kg. So this is your objective function which you are trying to minimize. Now, subject to the constraints, what are the constraints you have? That at least 36 milligrams of iron and there should be 88 milligrams of proteins. Now, bran contains 80 grams of protein. So 80 grams of protein. So 1 kg of bran contains 80 grams of protein. So x kgs of bran will contain this much of protein, plus rice contains 100 grams of protein. So this much. Fine. So this total has to be more than or equals to 88. Fine. Then the iron, 36 milligrams of iron is total required, of which 40 milligrams of iron is given by bran and 30 milligram is given by rice. So that has to be greater than or equals to 36. So this is your question, right? Now, whenever we are having minimization problem, we have to be careful that we have this inequality. That is, we have the greater than equals to type inequality. So in that case, when we are drawing the graph, whenever we are having minimization problem, there will be few extra things that we have to do, which is bit different from a maximization problem. We are coming to that. So let us first draw the graph. Now in this case, as you can see, 80x plus 100y, this is the question given. So I can just reduce it down a little bit by dividing it by 4. If I divide it by 4, this becomes 20x plus 25y greater equals to 44. So let me just, this becomes 20, this becomes 25, this becomes this becomes 22. And if I divide this by 4, I can't divide this by 4, I can divide this by 2 only. So 20, 15, 18. So this is all I can do. Now drawing this graph is going to be a little bit difficult because given the criteria, the way it is given, it is going to be a bit difficult to draw. Now if you draw, please just go on checking. If you draw the graph will come something like this only. So it will come something like this. Now just to give you an idea, this will become 22 by 20. So 22 by 20 is something more than a little bit more than your 1, and this is 22 by 25, so that is a little bit less than 1. This is 18 by 20, which is less than 1. So let me just write this down. So this point is 18 by 20 comma 0, and this point is 22 by 20 comma 0, right? And where did I go? This is 22 by 25 and this is 18 by 15. So this is 22 and this point is, right? A bit confusing given the figures are very complicated. Now in both the cases the arrow is this side. So as the arrow is this side, which is away from the origin, so therefore what happens, the feasible region is actually unbounded region. So this is called, this is a case of unbounded feasible region. Feasible unbounded feasible region. Now whenever the region becomes unbounded, please don't go by these numbers. These numbers can be different, but let us talk about this unbounded feasible region. Whenever the region becomes unbounded, then whatever we have done for the previous problem, we will do all the same thing, but we have to do another extra step. Fine. Now let us understand what we mean by corner points here. Now you see in this area, this unbounded region, we can't have any other corner points. So what are the corner points we have? This is one corner point, this is one corner point, This is one corner point. So this is one, and this is one. These are the 3 corner points. Fine. So now we will do the same thing. We will be trying to find out the corner points first. I mean this middle corner point, and then we will be drawing the table. So let me do that. So let me do something. Let me erase this part. Oh, what did I do? Anyway, let me just write the equations all over again. So it was 20x plus 25y equals to 22. Let me keep it like that. And this was 20x plus 15y equals to 18. So this was the question. So minus minus minus. So this was 10, 4. Y is 4 upon 10. And if I put this somewhere, let me put it here. So 25, if I put y as 4 by 10, 25 into 4 is 100. 100 by 10 is 10. 10 goes on the other side, it becomes 12. So x becomes 12 by 20. So therefore this point, 12 by 20 and 4 by 10. Don't be scared of the figure. The figures can be a bit scary in different problems, but if you are doing your calculations correct, I'm pretty sure you won't be having much problem. Values of z. Fine. So let us just write those points. So one is 0, 18 by 15, then 12 by 20, 4 by 10, and the next one is 22 by 20, 0. Now I have to do this calculation. So 0, 4 into 18 by 15, so that is 72 by 15, which is 4 point something. Then you can cancel it by 3 also. If you cancel it by 3, this is 24 by 5. So this is 4.8 actually. Fine. 12 by 20, if you put 12 by 20, if you just cancel it out a little bit. So if you cancel by 4, it becomes 3 by 5. So it becomes 3. And 16 by 10, that is 1.6. So that is 4.6. And if you put 22 by 20, so 22 by 20 is actually 11 by 10. So 5 into 11 by 10, that is 11 by 2. So that is 5.5. Something like that. So therefore, this is your minimum. I am looking for the minimum. Remember it. So this is your minimum. Fine. Now, you will say that I am done. No, I am not done. Why? As this is unbounded feasible region, there can always be a possibility that there can be a solution in this unbounded region. I don't know. Or there could have been another corner point in this unbounded region. I don't know. So to ensure that this point is the one which we found out, that this point is our solution, we have to do another extra step. What is that extra step? 5x plus 4y is giving me the minimum value at 4.6. So what I will do, I will draw a line 5x plus 4y less than 4.6 on the same graph. Fine. And we will check that if this particular line or this particular region has anything common with the unbounded region. If this line has got anything common with the unbounded region, then I will say that whatever I got as the minimum solution is not the minimum solution. Why? Because what I am trying to draw here, you see, 5x plus 4y less than 4.6. That means what? I am trying to draw that region which is less than the value 4.6. If that value coincides with this unbounded region, that means what? There are possible solutions which are less than 4.6. So that means what? I am not getting the minimum value. If it does not coincide or if it does not intersect with this unbounded region, then I can say that this 4.6 is the minimum solution. Now, if I draw this line, you will see that the line passes through somewhere here. So this is the line, this 5x plus 4y less than 4.6. Why dotted line? Dotted line because it is a less than inequality. If this would have been a less than equal to or greater than equal to inequality, I would have drawn it with solid line. But if I have less than or greater than inequality, ensure that we are always going to draw it with a dotted line. And this has to be shown pretty much. Now you can see this dotted line does not have anything common with this unbounded region. You can see it is passing through here. It is nowhere nothing common with this unbounded region. So now I can say, obviously we have to say this. This extra line that I have drawn on the graph, this is called the open half plane. This is called the open half plane. So therefore we will say that as the open half plane, let me just do something. If this graph is clear, let me just erase the graph because the work of the graph is over. Now the writing part. In this problem, writing is very important. So I will write as the open half plane which is 5x plus 4y less than 4.6 has no common region with the feasible region or no common area. Let me write just no common area with the feasible region hence the minimum, this is your what I am trying to do, the minimum cost is equals to rupees 4.6 and amount of bran required, that is your 12 by 20 kg, so that is equals to into 1000 if you do, so 12 into 50, that is 600 grams, and amount of rice, that is equals to 4 by 10 kg, that is equals to 400 grams. Fine. So this is your answer. Fine. So please ensure if you are given such kind of a problem, in case of minimization problem, your final answer must include this part. This is very important. Fine. Okay. Now let us move to the third and the final problem, that is the transportation problem. Now allocation problem is almost the same as this diet or manufacturing problem. Either it will be a maximization problem or a minimization problem. Now let us move to transportation problem, which is a little bit different. So let us take the example on your screen and then we will be solving it. Now you have seen the problem on your screen. Now this is the table which is given. So what is this table? There are two factories and there are three depots. So from the factory you are delivering the items to these depots and this is the cost given. Fine. This is the cost of transportation per unit of the depot. Fine. This is what it is given. Now you have to devise a problem, a linear programming problem, such that given that there is a total capacity of items that can be stored in the depots and there is a total capacity of items that can be sent from the factories. Given all these and the transportation cost, I have to ensure that this transportation is taking the minimum cost. Fine. So that is what it is given. Now let us do what? Let us just read it once first. It is given that from the two factories A and B, the commodities are to be delivered to the depots in C, D and E. The requirements of the depots are given 5, 5 and 4 and the capacity of the factories are given 8 and 6. So now you have been given this transportation, so you have to find what is the minimum cost of transportation. Fine. Now I have to draw something, that is, this is C, this is D, this is E. These are the depots. This is factory A, this is factory B. Fine. Now A is sending some items to C, I mean the commodities, some units of commodities. A is sending to D, A is sending to E. Similarly, B is sending some item to C, B is sending some item to D and B is sending some item to E as well. Now obviously it is not necessary that B has to send items to all the three and A also has to send some item to all the three. It matters is that the total capacity of the factories A and B and the total requirements of all these three depots must be fulfilled. In which manner it is getting fulfilled, that is exactly how it is going to determine the cost is going to be less. I mean the minimum. So now A has got a capacity of 8. Just see, A has got a capacity of 8 and B has got a capacity of 6. So A can at most send to anywhere 8 units of the commodity. B can send at most anywhere 6 units of the commodity. Now CDE has 554 requirement. So C requires 5, D requires 5, E requires 4. Right? You see 8 plus 6 is 14, 5 plus 5 plus 4 is also 14. So that means that whatever the total amount of commodities the factories have, the depots have the exact same requirement, that has to be equal. Now let us consider A is sending to C some X number of commodities. I don't know how many. Let us consider A is sending to C X number of commodities. Then what will happen? A is sending to D some Y number of commodities. Let me consider. I can consider at most 2 variables. I can't go beyond that. So, how many items A must send to E? Obviously, X and Y number of items have already been sent to C and D. A has the capacity of 8. So, it can send at most this many items. Clear? Similarly, C requires 5. A has already sent some to C. How many? X. So how much more does C require? 5 minus X. So that 5 minus X must come from that 5 minus X. That 5 minus X must come from B. Similarly, A has sent Y number of commodities to D. So B must send rest, so that is 5 minus Y. And similarly, E requires 4. A has sent this many, so B must send 4 minus 8 minus X minus Y, so that is your X plus Y minus 4. Right? 4 minus of this is giving you this. So now once I have got how much of the commodities are being sent from the factories to the depots, now let me model the LPP. So how to model the LPP? Now this is a little bit cumbersome, so let me just write it here on this side. So as it is a cost problem, transportation cost, it is a minimization problem. So this is mean Z equals to. Now I have to add up all the cost of transportation, right? So therefore, look at the table. A is sending an item to C, it is taking 160 rupees. So therefore, if A is sending X number of items, so it will be 160X, right? Plus A is sending Y number of items to D, so there it will be 100Y. Then A is sending this much item to E, so it will be 150 into 8 minus X minus Y. Fine. Then again, B is sending 5 minus X items to C, so it should be 100 into 5 minus X plus 120, so that this should be 120 into 5 minus Y. Just go through the table once. The table is given. I am just writing these values from the table only. And then B is sending this much to E, so that is again 100. So 100 X plus Y minus 4. So this, once you add up, gives you the objective function. So let me just add up for you. So this is going to be really a tough job for me. So let me just do it. 160X minus 150X, so that is 10X, minus 100X minus 90X plus 100X, so plus 10X. So this gives me 10X plus 100Y minus 150Y, so minus 50Y, minus 50 minus 120, so that is minus 170, minus 170 plus 100, that gives you minus 70Y. And then there are certain constants also, so we have to add them. 150 into 8, that is 1200, 1200 plus 500, that is 1700, 1700 plus 600, that is 2300, and 2300 minus 400, that is 1900. Please ensure, I may be wrong in calculation, I am doing it orally. Please ensure if it is correct or not. Just check it once. So this is your objective function. So I was telling you some objective function can have constant part. So this is one example where there is a constant part. Now once we have this comes the constraints. Now the constraints will be, subject to the constraints. See this, writing the constraints in case of a transportation problem can never be easier. All these values that you see, if you just put greater than equal to 0 in all of them, or greater than equals to 0 in all of them, yes, because these are all positive quantities, you will get all the constraints, right? So first one is x greater than equals to 0, which is obvious. Second one is y greater than equals to 0, again obvious. This is called the non-negativity constraint, which we already know. Then is 8 minus x minus y greater equals to 0, then 5 minus x greater equals to 0, 5 minus y greater equals to 0, and x plus y minus 4 greater equals to 0. So these are the constraints in the problem. So once we have already written the constraint, once we already have the objective function, let me erase this and write the whole problem in the way which we already know. So work of this figure is already over. So therefore my problem is minimize z equals to 10x minus 70y plus 1900 subject to, now 8 minus x minus y greater equals to 0, so that means x plus y less equals to 8, so that is one constraint. X less equals to 5, that is another constraint. Y less equals to 5, another constraint. And x plus y greater equals to 4, that is the fourth constraint, and x and y greater equals to 0. So you see, after all the hard work that we have done, the problem reduces down to something like this. Let me just erase this. So in case of a transportation problem, the modeling of the problem is all that requires time. But after this, I think you can easily solve it. You have to draw the constraints and you have to find the corner points and you have to solve. So let me just do it for you. This is y, this is x, this is 0. X plus y less equals to 8. The line goes somewhere here. So this is 8, 0. This is 0, 8. X plus y greater equals to 4. Parallel line. This is 4, 0. This is 0, 4. Right? X less equals to 5. X less equals to 5 means if here there is 5, this is how the line x equals to 5, so it doesn't matter. Y less equals to 5. Now I think I have drawn a little bit wrong, because 5 will be here, it will go somewhere here, 5 will be here. Now here there will be 5, 5. No, it can't be. Something like this. It should be a square, but the figure went a little bit different. So this is 5,0, this is 0,5. Now we have to find the region, which is the required region. Now my figure doesn't look very good, so please excuse me for that. So this is this side, this is this side, this is downwards, this is inwards. Fine. So therefore my feasible region should be this one. My feasible region should be this one. Now as I haven't managed to draw the figure properly, so in that case I am a bit confused with which part has to be inside and which part has to be outside. Please ensure you do it on a graph paper and find all the corner points. Now here, as there is no unbounded region, we don't have to take all the trouble of drawing that open half plane and all those things. It's simple that we will be just writing the corner points and the values of z. Whichever comes as the minimum value is going to be my answer. Fine. So that's it. That is all we had in this chapter, and most of the time this type of problems don't come in the exam. They just keep their problem restricted to manufacturing and diet problems, but still these are pretty fun to work with if you have some interest. So give it a check. Fine. So thank you so much. As always, if you have any doubts, get it clarified. Thank you.